Now, you already know that the nucleus of an atom is made up of protons and neutrons. Protons have a positive charge, neutrons are neutral. The term nucleon is a more general term that applies to both protons and neutrons because they are what make up the nucleus. Remember that each atom has an atomic number, which we call Z, and it has a neutron number, N, and a mass number, which we call A. So the atomic number is the number of protons in that atom. The neutrons are N and the mass number is A, so the mass number is just the atomic number plus plus Z plus N. Gosh, I can't write. Z plus N. There's a particular notation we're going to use to denote the composition of a nucleus. For example, for carbon-14, we'll write C is carbon, of course. The atomic number is 6, and it's carbon-14, which means it has a mass number of 14, which means it has 8 neutrons. But so we write it like this: 14, 6, C. And this stands for carbon-14. There's an atomic number of 6, mass number of 14. Okay. So in general, for some atom X, it's again mass number, atomic number. That's confusing because Z is atomic, and you think A would be atomic, but A is the mass number. So just don't get confused about that. Sometimes it'll be written just like this because you can consult a periodic table, or just remember that carbon has an atomic number of 6, but we're always going to write it with that extra subscript down there. And remember, different isotopes of an atom have different numbers of neutrons and therefore different mass numbers. So there's a carbon-14 and there's also carbon-12, and there are different isotopes of different atoms. A proton and a neutron have approximately the same mass, and that has led to the common usage of the atomic mass unit. Which we will abbreviate with U, and one atomic mass unit is 1.660540 times 10 to the minus 27th kilograms. And this is what the mass is going to be important a little bit later on when we're going to be using Einstein's famous equation, the E equals mc squared, to figure out how change in mass leads to change in energy and so forth. And following from E equals mc squared, then mass is equal to E over c squared. So it's also useful to identify this mass as an energy per c squared. It's 931.5 mega electron volts per c squared. And this is handy. You could divide this and get a number, but what's handy is that if our energy is mc squared and we have our mass defined in terms of c squared, then if we plug this in as our mass, we'll get an energy just by canceling out the c squareds. So that's going to make our lives a little bit simpler. Now, we know that nuclei, being composed of protons and neutrons, that means that nuclei are positively charged. We also know that positive charges repel one another. So if electromagnetic forces were the only ones going on, our nucleus would fly apart. Now, our nuclei don't fly apart, which we can tell by the fact that, we're here and there is matter. And what holds nuclei together is called the strong force. Very creative name based on the fact that it is strong than any of the other fundamental forces. uh, the strong force, it is an attractive force that exists between nucleons. And it's been quantified and all that, but it is not all that well understood, and it's not understood at all in terms of why that force exists, other than, it needs to be there to hold nuclei together. It appears to act only between protons and neutrons, so it doesn't, yank any electrons out of their orbits, and it only acts over very short distances. Only acts over very short distances, on the order of 10 to the minus 15th meters, which is about the radius of a nucleus, which is on the order of the radius of a nucleus. So that's good. As atoms get bigger, atoms in general. As atoms get bigger, the nucleus gets bigger, and at a certain point, that it gets outside the bounds of how big of how far the strong force can act over, and the electromagnetic force starts to get closer to the strong force. And eventually, these atoms become unstable. So if an atom has enough protons, its nucleus is unstable. Though this effect is somewhat, diluted isn't really the right term, but it's somewhat diluted if there are more neutrons. Because if there are more neutrons, there's more strong force. But there is more electromagnetic force as we get more protons. So, and as it happens, then an unstable nucleus will will have some form of radioactive decay. It will radioactively decay in some way or another, depending on what it is. And there is a cutoff point on the periodic table where all atoms with atomic numbers higher than, what is it? I think it's 92. I think everything with an atomic number higher than that is unstable. I think there is a stable isotope of uranium, I want to say, and that's the last one. But it might be even lower than that. I don't know. I'll have to double check on that. But unstable nuclei will experience radioactive decay. Now, when this happens, when decay occurs, mass is not conserved. Classically, the conservation of mass was one of the fundamental laws of the universe. But in quantum mechanically, it isn't just mass that's conserved, it's this combination idea of mass and energy together being conserved. So there is, you have some mass in your nucleus, and then some form of radiation occurs, and then you have that's a poorly drawn, a somewhat smaller nucleus. Anyway, but the mass of these two does not equal the original. There is some mass that is converted into energy. Okay, and that is according to Einstein's equation. The change in mass, however much mass is lost is converted into energy. There are, you could say I don't know, there are kind of like 3.5 types of radiation. Or types of particles that are given off. The first is what's called an alpha particle. And this is the Greek letter alpha, little fishy thing. Alpha particles are helium nuclei, which means there are 2 neutrons, 2 protons. That's what's given off in alpha decay. And they're classified according to how dangerous they are based on how much they can penetrate through different materials. An alpha particle will penetrate a sheet of paper just barely. So it can't get through very much. There's beta radiation. These correspond to the first 3 Greek letters, alpha, beta, and gamma. Beta particles, which are electrons or positrons. Positrons are the antiparticle of an electron. They are identical to electrons, except that they have positive charge. So they have the same mass, same magnitude of charge, and all that fun stuff, but they just have a positive charge. So electrons, we say, is beta minus or just beta, because electrons are more common. It's more common that a beta particle will be an electron. And positrons are beta plus. And beta particles will penetrate a few millimeters of aluminum. So they are more penetrating than alpha particles, thus more dangerous, but still not too bad. Gamma radiation is the gamma rays that we talked about when we were talking about the electromagnetic spectrum. And this is the most dangerous. And a gamma ray can penetrate several centimeters of lead, which is more difficult to penetrate than aluminum. And just for the sake of you knowing, alpha, beta, and gamma are the first 3 letters of the Greek alphabet. And I think that may be why gamma rays are the only kind of electromagnetic radiation that are given a Greek letter, because they were originally named in relation to talking about them as radiation, not as in terms of the electromagnetic spectrum. And we're going to look more in depth at each of the different types of radiation coming up here.